OneX Developer Podcast.
Hello, and welcome back to the OneX Developer Podcast.
I'm Brendan.
And I'm Colin. I guess I always introduce myself first, don't I?
That's okay, because you do the intro. I feel like that, you have the momentum.
Yeah, okay. Today we have a very special episode. We're going to be talking about a little programming language called APL, which Brendan is an expert in.
Never heard of the thing. Are you sure it's APL or is it Apple?
Whoa, that's crazy. I can't even think about what it stands for right now. I know I looked it up.
I looked it up, and according to the Wikipedia page, it's a programming language.
Really?
Yeah.
I could have I thought it was like array something because that's part of it, but whatever. Dang. Okay, so Brendan and I both know very little about this, but basically, I came across APL, and I am just kind of enamored by how weird it is as a language, and I wanted to do an episode talking about it. So I thought it'd be a cool idea to just kind of like go through an intro tutorial and just like see what happens. So it's gonna be a little bit of a different episode today. But first of all, before we even get started, let's do a shout out to tryapl.com because they're gonna make this whole episode possible. I think I saw, yeah, we got credits here. Shout out to Brian Becker, Brian McCormick, Will Robertson, Richard Park, Adam Brzezinski, Joel Hu, John Scholes, Andy Shires, Roger Hui, John Daintree, Sean Gilchrist, all of these people for working on tryapl.com, which is what you see here. That's what we're going to be using to try to learn this language.
Do we want to talk at all about what little we know about APL before we dive in?
Sure, yeah. I mean, I've looked at this a little bit, like messing around with this tool and stuff to just like before we get started. And I mean, so the thing that drew me to it is like there's all these weird symbols, right? Like this is gonna be a tough episode for the audio listeners. I just realized, but the language is built on like all these like crazy bonkers symbols that like all represent different things, and so you end up with this code that like looks like alien language, and that just like blows my mind. So
it really does look more like mathematical notation than most programming languages. It looks it takes full advantage of like symbols that you don't find on your keyboard, basically. And that's kind of the thing. I don't know if you know the answer to this, Colin, but like first of all, APL is a very old language, right? It goes back to the 60s. When people were programming APL back in the day, were there dedicated terminals with special keyboards and stuff that had these characters on it?
There were special keyboards. I know that was a thing at one point. Nowadays, I think people are mostly using like software tools that allow them to do like key bindings for all the different symbols and stuff.
Mm-hmm.
So that's the value of using something like tryapl, right? Is that I don't have to install any of that stuff. I can just be in this little terminal in my browser, and I can like click these buttons, or there's like key bindings for them, and like everything that I want to do is like right here to mess around with.
Yeah.
Yeah, I did look up some pictures of like the APL keyboards and stuff, and yeah, there was a thing. They had keyboards that had like, they had the full alphabet, QWERTY stuff that you expect, and then like, I guess there was like a super key and like with a symbol next to it and stuff. So there's all these like runes kind of on each key next to the letters that you would expect.
That's a big ask, man. You make a new programming language and you're like, but the thing is, you're going to have to buy a new keyboard.
Yeah. Yeah.
The only other thing I know about APL is that arrays are the primary data type, right? Like every
Yeah.
operation you do is on an array of numbers. You never like operate on a single scalar number, right?
Yeah. Yeah, that's right. It's all like array focused. And so I guess that's also something to point out is that like APL, I believe right now is something mostly just used by like hobbyists and like kind of language nerds. Like, I don't think people are really building like production software with this. I don't think that's really. I don't think it'd be really be suited for that today. I do know that there are languages like there's one called BQN, and I think there's another more popular one which is meant to be kind of an APL plus plus kind of thing. That makes it a little bit more like modernized and stuff. But yeah,
Cool. I'm looking forward to it. I'm looking forward to learning something today.
let's just read the intro here. So, got a minute? Try APL. APL is an array-oriented programming language that will change the way you think about problems and data. With a powerful, concise syntax, it lets you develop shorter programs that enable you to think more about the problem you're trying to solve than how to express it to a computer. Try APL runs on Dialog, which you can download for free or try it now by entering an expression. Use the language bar above to type the special APL symbols, or clicking one of these expressions below to press enter. So I think this is actually a good place to start because this is kind of fun, right? So it shows us like, okay, 2 plus 2 equals 4. That's kind of what we expect. You can add. So like, okay, so this is interesting right here, right? When you add these space delimited numbers, these are treated as arrays, right? So it's not 423 plus 857. It's 4 plus 8, 2 plus 5, 3 plus 7. So that's like your first taste of like what array oriented means.
So yeah, a list of numbers separated by spaces is treated as an array.
Mm-hmm. And here's our first taste of a word symbol. By the way, also all these symbols have names, and I don't know them. So like this one, it stands for indices. I don't even know. Is that like a Greek symbol? I don't know. Looks a little bit like a lowercase I, but it's called indices. Or like that's like the keyword representation. And so basically, it just did it took the indices 1 through 10, right? If I do indices 10, it prints out 1 to 10.
So, I mean, right there you can see incredibly compact. Like the equivalent Python line would be something like for I in range 0, 10, something like that.
Yeah, yeah, and that's in Python, which is known as being very concise.
Yeah. Interesting. That's fun.
So this will sum the first 100,000 integers. It's plus sign over indices 100,000. I'll take your word for it that that's the right number. Wait, is that right? 100,000? Probably, right? A long, slow way to write factorial 10 would be x over. Wait, what just happened? Hang on. Let me try that again. Okay. X over indices 10, that would be factorial 10, I guess. And that's one thing I wanted to point out that is I realized is kind of a weakness of APL specifically is you have symbols like this X, which is not an X, right? So like, I don't know if you can see the difference. Like if I type X, that's like X on my keyboard. And then I use the times symbol. You can see these are actually two different symbols. Do you see that?
Yeah, they're a little hard to differentiate.
Right, yeah. And it's the same thing with like even that plus I think is different from. Oh no, that's actually the same one, I guess. but that kind of stuff can happen, right? And that's kind of like, oh, uh, okay. I think BQN and some of the newer things are supposed to like remedy that a little bit.
Hmm. Yeah, that is interesting. I mean, yeah, that conciseness that we were just talking about is like that seems like it can also lead to some confusion. Um,
Yeah, and
just
we're going to
typing.
get into that. We're going to get into that for sure. Like, let's look at this next example. Okay, average is the sum divided by count. That's this whole string here. So this is like an assignment, I guess. Um, the sum. I forget what this symbol does. I mean, this is just the intro. We'll get into this in the tutorial, but like, oh damn, do I have to do? I don't know why it's not. What the hell? Did I do something wrong?
Compile.
What if I just? Ooh, that doesn't seem right. Let me refresh this. This is what I was afraid of. Oh, oh, I'm an idiot. That's just an assignment, so it doesn't print anything. We got to then do this.
Gotcha.
And then do it. Right. So that defined average as this function. And then we did the average of 1, 6, 3, and 4, 3.5.
Curly brackets are defining a function.
I think so.
Okay.
On that note, let's go ahead and jump into or let's skip some of this stuff. I just kind of want to show that one off because it's like, yeah, look how funky things can get quickly. But let's read this real quick. What can APL do for you? Are you a problem solver or a programmer? Problem solvers benefit from APL's ability to concisely express advanced concepts without getting bogged down with lots of computerese syntax. Programmers benefit from APL's productivity and brevity. Shorter programs means quicker development times and less code to maintain and debug. That's a little bit of a spicy statement, maybe.
Yeah. Yeah. I think there's such a thing as too concise, but I'm going to hold off judgment until the end.
In either case, concepts that take several lines of code in other languages can often be reduced to a few characters in APL. You'll quickly find that APL symbols are organized in a logical, mnemonic manner that makes it easy to express advanced concepts clearly and concisely, and makes it easy to learn too. Move to the Learn tab and get ready to start, or visit the Primer tab to explore. So let's go ahead and get into. Okay, so the primers is kind of like a cheat sheet thing. We want to learn. This shows you how to use the tutorials. I don't think we need to do that. Let's go ahead and get into APL expressions. Now we can really get started here. Again, I think we made this clear, but let's go ahead and just be clear. Brendan and I do not know APL, if that's not obvious yet, right? So we're two guys that are fumbling our way through this.
Yep.
APL is a mathematical notation that just happens to be machine executable, i.e., be a programming language. So there you go. That's your APL. It just seems like it's the first thing they say about it is it's array oriented. It just feels like A should stand for array.
APL subverting expectations at every turn.
Yeah. APL expressions consist of functions, arrays, and assignments. They may also have trailing comments beginning with the lamp symbol. This is one of the names that I know. This thing is, I kind of like it because I think it kind of looks like the Among Us guys. Kind of looks like Among Us. It's called lamp because it looks like a lamp.
Oh, the game. Yeah.
Yeah. With the little dudes with like the astronaut thing,
Yeah, I'm with you now.
Kind of looks
Okay.
like Among Us.
That's a comment?
That's a comment. Yeah, is this, and we'll see it here. Yeah, this is a comment. Nothing happens. So yeah, comments have their own symbol.
Interesting.
You can have multiple expressions on a single line by separating them with a diamond. So 2 plus 2 and 3 plus 3 are two different expressions that are just put on one line using this diamond syntax. What do you think so far, Brendan? We haven't seen much, but
It's kind of funny. There's a part of me that sees the diamond and it's like, just use a semicolon. But it's like,
yeah.
but at the same time, it's like, I don't know why. What's special about a semicolon? Why not a diamond?
Well, semicolon is on your keyboard.
Fair enough.
But yeah, but also I also wonder, like, I mean, a language that was, you said this was made in the '60s, right? Like,
Yeah, I think I read. Yeah,
semicolon probably wasn't like, I mean, C was made in the '60s too, right? So like, I don't know, maybe semicolon wasn't like a defined thing, so they were just kind of, there wasn't so much. What's the word, like? There wasn't like inertia behind any of these symbols, right? Like people were kind of just doing what they wanted to do. Maybe
right.
I don't.
Yeah, no, I think that's exactly right. I think that's kind of what I was trying to say is like, I bet there were a lot of different ways to do that same thing, and it just so happens that most of the languages that we use on a day-to-day basis kind of trace their lineage back to C, and because
Yeah,
of that have the semicolon, and that kind of like it kind of won out in that war or whatever. But like, yeah, I'm sure that a lot of different languages that were being developed at that time, you did it a lot of different ways. Nothing special about
there's another
semicolon.
universe where we're using diamond at the end of every line.
That's right. Diamond button
Functions.
on
We
my
call
keyboard.
all code that can be applied to data functions, even primitive built-in things. So plus and f in f of x are both functions. APL operators are something else. I don't know what that means, but let's just go with it. All right, there's a plus. There's minus 5 minus 2, 3. Okay, we already saw this. Many APL functions can be applied as prefix monadically or infix dyadically. A lot of syllables here. Usually the monadic and dyadic forms are closely related. So all he's saying is, yeah, like this example here, right? So I can do monadically, I can say -3, which that, right, that's when the minus sign is up like that, that's negative, I think. But I can also do 0 -3 dyadically, and that would also be -3.
So -3. So the monadic one, there's an implied zero there. Is that what he's saying basically?
I think that's what he's saying, yeah.
It's okay. The monadic
Functions can be
version.
applied as prefix, right? This would be a prefix or infix dyadically, yeah. I
Okay,
think that's basically all he's saying there.
cool.
Um,
That's kind of neat.
yeah, and then he explains APL uses high minus to indicate negative numbers.
High minus.
So that's what this is, right? This minus sign that's like up a little bit.
Hmm.
I wonder why. I guess, I wonder if that was like just a limitation of, like, maybe in the language that makes more sense, right? Because then you have a separate symbol for negative numbers versus an operator, right?
Right.
Maybe that's all that is.
Right. Because when you write -3, that's a
That's a function.
monadically applied function. You're saying apply that function to 3, and you end up with the value -3, and those are
Right.
two different things. Okay.
Yeah. Conceptually, those are two different things. Um, we saw a comment there. I really like this. I think more languages should use the lamp symbol. I like it.
Huh.
All data resides in arrays. An array is a rectangular collection of numbers, characters, and arrays arranged along 0 or more axes. We can use more specific terms for some arrays, like a single number is a scalar, a list is a vector, and 2D arrays are matrices. Vectors can be formed by just placing elements next to each other, which is what we saw earlier. Yeah, like this. 1, 2, 3, that's an array.
I think that's kind of neat. I think that's I this is the concept that is most intriguing to me so far. Is just that arrays being so primitive to the language, so um, you know, essential.
Yeah, and so at this point, I started wondering, like, so I believe we probably should have mentioned this earlier. I believe a lot of the history of APL is with like financial companies and stuff, like more that kind of thing. But when I get to this stuff and I start seeing like all this like built-in support for like crazy array stuff, and especially when I see mentions of matrices, I start thinking like game development, right?
Hmm.
And I don't think APL is suited for that. I don't. I mean, I don't know what it performs like, and it's a very old language. But I do wonder if like some of these ideas could be incorporated into like game dev type things, right? Because if you're making a 2D game, matrices is like, no pun intended, the name of the game. Like that's like what you're doing all day.
Right. Yeah, totally. The way that GLSL has Vec3 as a built-in type, basically.
Right. Yeah. Strings. As APL has no string data type, we just use character vectors or lists instead. Characters and character vectors are in single quotes. So A, that's a that's not a string, that's a vector of characters, but effectively a string. Hello world. Numbers. A number is a number is a number. You don't have to deal with internal representations, as APL will internally convert between bit booleans, integers of various sizes, floats, base 10 decimal floats, and complex numbers, all seamless to you.
That's interesting.
I
I
didn't
mean,
know this. Let's see the example. 5 greater than 4, 1. 1 is true, by the way. I didn't know that. Bools are just 1 and 0 in APL.
okay.
2 plus 5 greater than 4. That's kind of weird. Wait, am I thinking that right? Is 5 greater than 4? Does that mean something? No, that just means greater than. Okay. Uh, you can just do 2 divided by 3 and it gives you a decimal. That's cool. And then you can just add an integer to it, right? There's no problems with conversions there. That's nice.
Mm-hmm. That is nice.
APL takes care of binary versus decimal inexactness too. So 3 times the term 1 divided by 3 is really 1.
That is really nice.
Yeah, that is nice.
I mean, even in Python, you have to like import
Yeah,
decimal or whatever.
yeah, you can't just do that in. I don't know of any other language where you can just do that. Actually, there probably are, but I can't think of one.
I mean, this is kind of interesting though. This feels a little JavaScripty to me, right? Like JavaScript has, just has until recent years has it just had like a number type, and a number could be like
Yeah,
a decimal or an integer or whatever. And like I don't know how they're represented internally. I think they're all floats internally or something. But like um this this not really caring about the specific representation of the number is that feels very like high level language to me.
yeah, and I think this makes sense. Like you mentioned that a lot of it looks like math, and that the history being financial. I think this makes a lot of sense, right? Like because this is basically what you expect like your graphing calculator to do, right? Like
Right.
if you're thinking in math terms, you're thinking 3 times 1 over 3, 1, right? Like very obviously should be 1 from like a human's perspective.
Yes, absolutely. And I'm sure that that's tripped a million people up who are trying to learn programming over the years, is when that same result in C would, be 1e negative
Yeah,
34 or whatever.
yeah. Negative numbers are indicated by a high minus. We've seen that. Very large or small numbers use exponential notation, separating the significand from the I think these are new words to me. Have you seen these words before?
I've heard of the
Mantissa?
mantissa. Yeah, I don't know how to say it, but it's in scientific notation, it's just the part before the E and the part after the E.
Right, right, yeah. I'm just saying this tutorial makes me feel a little inadequate. a little bit. In other words, oh, there we go. Just keep reading. In other words, a capital E embedded in a number reads as 10 times 10 to the power of. So all that to say, 1E12 is like what you expect.
Yeah, cool.
1E negative 6 is like you expect, right? Yeah.
Is the high minus character, is that the one like on the far right of your symbol list there?
Yeah.
Okay.
Negative. Also, a cool thing about Try APL, the tool, is that there's like keystrokes for all this. So I can type minus minus tab, minus minus tab, and it'll do the thing. That's what I was saying before we started recording. I wanted to learn some of those before we started, but if we just go through the tutorial, it kind of does everything for you, so it's fine.
Cool.
Complex numbers are similar in that they use a J to separate the real and imaginary parts. Ooh, I like that. Okay, I'm just like I'm having a nerdgasm, you might say. So you probably learned imaginary numbers as having lowercase I, right?
Right. Yeah.
Yeah. So this is a thing. So like yeah, like the imaginary number 10, it would be like I10 or whatever, right? Or 10I, what I don't know. So in electrical engineering, and I believe only in electrical engineering, we use J because I is already used as the symbol for current in electrical engineering.
Ah.
So they use J, and I think it's just because it's J comes after I in the alphabet. Um, and I remember in college telling a math major that we did that, and she was just utterly disgusted. She felt like she felt very strongly that all imaginary numbers should be notated with a lowercase I. And so anyway, I like that we got a J in here.
That's interesting. I wonder what the so in electrical engineering the rationale is that I is already used for something else. I wonder what the rationale is here though.
Yeah, yeah, I wouldn't know.
Maybe it was made by electrical engineers and they thought that's just the right way to do it.
Yeah, I really don't know because I don't unless I is like a reserved character for something else. I can't imagine any other reason why other than just like preference. Maybe they felt like it was a bit more readable,
Yeah.
easier to distinguish. Maybe I don't know. Oh, I just like copied something. Whatever.
Whoa.
Ignore that.
I think it's kind of funny of all the like unique and these weird symbols that we have. Complex numbers don't get their own symbol. Like it kind of feels like that should be.
No, there's a few times like that actually. I feel like when I was looking this up, there was a few times I felt that way. Um, yeah, that is a little odd. So then it looks like. So I'm not sure what happened here. Actually, they did 1J2 times 2J1, and then we got 0 capital J5. I'm not sure what the math actually is here. That's like one image. Does this make sense to you?
I don't remember how to multiply complex numbers to be honest. But I think, are you asking about capital J versus lowercase j?
Yeah.
I think that's interchangeable. Like I bet if you do 1 capital J 2 times 2 capital J I, you'll get the same result.
Yeah. That's what I'm hoping. Yeah.
Yeah.
So yeah, it can be capital J or lowercase j. Assignments. You can assign a function or an array to a name using left arrow. Whoa. Okay, so this is kind of cool what they did here. So not only can you assign a value with like the words 2 and 3, but you can even assign an operator to a function name like that.
Yeah. That's really interesting. And then use that in place of the function.
I wonder, can you do that with like everything? Like, can I do like? Okay, this is probably dumb, but can I do like comment, left arrow, or is it? Oh, it's all the way over here. Left arrow and then lamp. Can I do that? Missing right argument. Oh no, because that gets interpreted as a comment.
Oh,
Okay.
yeah, that's not a function.
Yeah.
Um, I gotta say, I kind of really like. I can't really explain why, but going back to our satisfaction episode, um, I really like the look of like right arrow assignment like that. That
Oh
feels
yeah.
good to me.
Me
Variable
too.
name on the left, and then I mean, I guess that's, that's how most of the languages that we work with work, but for some reason that looks really good to me. An arrow pointing that way for assignment.
Well, it looks good, and it is also really nice that there is a very clear difference between assignment and equality.
Right.
Like I can't, you can't confuse this with anything really.
Right. Yeah. The whole reason that we have double equal sign
Yeah.
to differentiate the test of equality versus assignment, all of that goes away when you have a unique um, symbol for assignment.
Yeah. And so it goes on to say that exactly. You can use equal as equal. 2 equals 3? No. Why use APL instead of conventional mathematical notation? Now we're getting into stuff. Mathematics has some inconsistent and weird notations, like negation and factorial being on opposite sides of their argument.
Hmm.
Never thought about that. That is weird.
That is weird.
Exponentiation doesn't have a symbol, right? Rather than exponent is raised and made smaller, which is something you notice if you've ever like. Well, I mean, it is annoying. Like exponents are annoying because you can't like type like that, but you can just use the caret symbol, right? And that seems fine.
Yeah.
But anyway, and magnitude has 2 symbols on either side, right? All of these things are things that are annoying from a computer perspective, right? Like if you're making a programming language and you're thinking, oh yeah, some of my operators are on the left, some of them are on the right, some of them are on both sides. That yeah,
Right. It makes it really, if you're trying to type that out, it makes it really hard to parse it as a
yeah,
line of code.
yeah.
Yeah.
APL harmonizes everything to be inline pre/infix single symbols. So factorial is exclamation point B. Raising to a power is A asterisk B, actually. Kind of weird. And magnitude, absolute value, is just bar B. Shows us those. Nice.
Wait, so remind me again, you used the okay. So multiplication is the times symbol, raising to a power is the asterisk. Okay.
Is that, and also I shouldn't say asterisk because asterisk is this. Oh wait, is that an asterisk? The font is like messing me up. Okay, it is actually an asterisk. Yeah.
Okay.
Which is weird, right? Because an asterisk would normally be multiplication.
Yeah. Although I kind of feel like, at least for multiplication, I feel like APL is more accurate. Hmm.
What do you mean?
The time symbol is more accurate than the asterisk for
Oh,
multiplication.
yeah, yeah.
Using the asterisk for exponentiation is a little weird, but
I agree.
I don't know. No weirder than the caret, I guess.
Yeah. Traditional mathematics also has a complicated and ill-defined order of evaluation. For example, is sine or multiplication evaluated first in sine alpha omega? How about in sine alpha cosine beta? And while functions that supposedly are on the same level evaluate from left to right, this doesn't apply to exponentation. And how about a divided by bx? APL has just one simple rule. All functions take everything on their right side as right, or only argument. Let's see some examples. So, 1 plus 2 times 3 is evaluated as you'd expect, right? 2 times 3 happens first and then 1. Yeah, so we're just evaluating right to left is what he's saying, right?
Right.
So this is 3 plus 1 and then 2 times 4. Right.
That's that I don't know. That's kind of interesting. There's only one rule in terms of order of operations, right to left.
Yeah. Let's keep going. You may, of course, use parentheses to force order of evaluation. Okay, so there is more than one rule, actually.
That's fair, though. I mean, yeah, you do have to have a way to do that.
Yeah. So in this case, it was the left group and then the right because there was parentheses. These rules apply to all functions, whether built-in or user-defined. Know the syntax of one, and you know the syntax of all of them. Hey, we got to the end of APL expressions.
Cool. That's super interesting.
Wow. I don't know how far we want to go in this. We got 2 more basic. We're at 35 minutes.
Let's do a little bit with arrays.
Yeah, maybe we could break this up into multiple episodes if we have to,
Sure.
like we did with the audio programming one. I do also want to before we wrap up, I want to take a little bit of a look at Conway's Game of Life. That's like the people really like to show off Game of Life in APL. Throughout this lesson, there are snippets of codes examples you are encouraged to edit and experiment with these. Okay. All data in APL resides in arrays. We know that. I think this is some review of the previous one. Yeah, we know all this already from the previous. Okay, so yeah, arrays, they work like what we talked about. Okay, APL. Yes, you can have an array of strings, or you can define one, or an array of characters, or you can define it all in one like this. That's the same thing.
Okay.
Whoa. Parentheses are used to group array items. Okay, so what's going on here? So this is one array with like subgroups?
Yeah, it looks like an array with 3 elements, right? The first element has 3 elements, the second element has 2 elements, and the third element has 2 elements. Is that right?
I guess this is an array of arrays, sort of. Okay, it's going to explain some more. Numbers are very straightforward. A number is a number. It doesn't matter if it is an integer or not, nor if it is real or complex. Negative numbers are used. Okay, yeah, we saw this already. The items of an array can be of different types. That's cool.
Oh, yeah, that is cool.
Hello, 100. Even in the subgroup, there can be different types within there. Okay, we got another one. An array has a rank and a depth. Okay. The depth is the level of nesting. For example, an array of simple, i.e. non-nested scalars has depth 1. An array containing only depth 1 arrays has depth 2, and a simple scalar has depth 0. However, for some arrays, it's not so easy. An array may contain both vectors and scalars. In cases like this, the depth is reported as negative. You can find the depth of an array with the function triple equal hamburger. What is this called? Depth. Called depth here. Match. Okay, so the depth of 1 is 0 because it's just a scalar, right?
Okay.
The depth of the array of characters APL is 1. Okay, that makes sense. The depth of this thingy is 3. Because we have, let's see, so like this is one thing. Wait, hang on. No, this is one thing. Right, because this whole thing is an array. Right, we've got two sub-arrays here, right? Let's do this real quick. If I just put this in here, we can visually see, yeah.
Oh, that's cool.
Right. So now it's like 1, 2, 3, right?
Right. Okay. So, okay. Yeah.
I don't know why it keeps doing like. I guess I'm not supposed to click around like this, but uh, so this has a depth of -2. It explained that. Uh, an array may contain both vectors and scalars. In cases like this, the depth is reported as negative. So this like one is a scalar and hello is a vector.
Uh-huh.
So I understand that it's negative, but why is it -2?
Sorry, I'm not following why it's negative. What does negative depth mean?
So I think all the negative means is that it's a mix of scalars and vectors.
Okay.
And I guess it's 2 because it if it wasn't a mix, it would be 2, right? Let's do the same trick again. If I just put this in here, right? So that's a depth of 2, and the negative just notates that there's a scalar as one of the elements, one of the top level elements.
That's throwing me. I'm gonna need to think about that for a minute. Um, but yeah, but basically, like negative depth isn't really like a mathematical concept. It's more just like APL
Right.
is reporting it negative so that you can, as an indicator that you can then do something with that depth. Is that right?
So if I do this, so this is just there's no scalars in here. But then the depth is 2. If I do this, just scalars, then the depth is 1.
Mm-hmm.
But if I mix, then the depth is -2.
Gotcha.
Okay.
And so if you did depth of a scalar value and then let's say a group of scalars in parentheses, would that also be -2?
Yes.
And what about if you put another group inside the parentheses?
If I did like this, or well, like this,
Yeah,
that would be
-3. Okay.
-3. Okay, yeah, I think I get it.
Yeah, I think it's coming together for me.
That's weird. But also like why would you do this? Like this isn't something you probably do a lot. Why would you need to know the depth of a array? Actually,
Uh,
that could be useful.
yeah, I have a feeling that that's going to be a common operation, almost like the length of a list, you know?
Right. And if you're doing a lot of array stuff, yeah. Okay, then there's rank. The concept of rank is very important in APL and isn't present in many other languages. It refers to the number of dimensions in the array. So far, we've only seen rank 0 arrays, scalars, and rank 1 arrays, vectors. You can, however, have arrays of other ranks. A rank 2 array, for example, is often called a matrix or a table. Okay, arrays are always rectangular. Each row of a matrix must have the same number of columns. Each layer of a 3D block must have the same number of rows and columns. As our screens are only two-dimensional, higher rank arrays are printed layer by layer. Creating arrays of ranks greater than 1 is only slightly harder than creating vectors. To do so, we can use the function row. It takes a vector of dimension length as a left argument and an array as a right argument. It returns a new array with the specified dimensions filled with the data of the right argument. If there is too much data, the tail just doesn't get used. If there is too little, it gets recycled from the beginning. Okay, there's a lot there. But basically, the rank is the number of dimensions, right?
Right.
So let's see some examples here. Okay. Okay, so we have two row, 1, 2, 3, 4. Okay, so
So
this is defining 2 rows, 2 columns, and then this is the array.
right. Yeah. So the vector dimension links are the left argument, and then the array is the right argument, and the array is either truncated or wrapped around if you don't do your math right.
So what does this have to do with rank, though? Like, Oh, because we defined the rank here. Let's see another example. 232. Okay, and this is what it was saying. If it's more than because a matrix, your screen can only really represent matrices, right?
Hmm.
So that's why we have two matrices, right? So we have like a 2x2 and then another 2x2.
Yeah. Okay.
Yeah. Okay. Okay. Three. Okay. All right. Let's just keep going. 3 row. Okay, so that's just columns defined, right?
So yeah, by giving it only a single value as the left argument there of 3, you're just saying an array with 3 elements, right?
Yeah. And this is an example of it.
Ah, yeah, yeah. Okay.
So okay. Okay, so now if we go back to this one, I'm a little confused now because we had a 3 here, but we only have 2 matrices. So I thought it would print like okay, if I do this again, but if I make it 222, what happens? Oh,
Each
the 3 is the number of rows.
right, each dimension
Oh,
only has 2,
okay. Oh shit.
and
I don't know what I
you
did.
get and a bunch of the data there got truncated um because the dimensions you gave were much too small for the data that you gave.
Yeah, messed up. Okay. Back. Okay. Yeah. So wait. So I guess what I'm not understanding is this the number of columns? The first number?
That's the number of rows, I guess. The second number is the number of columns, and the third is the third dimension.
8132. That would be okay. Okay. So if I did this, it would wrap around and fill in. Right. Okay.
Yeah.
And then if I did this, okay.
Each one has 3 columns now. Okay, yeah.
So wait, so this number is the columns. This number is the rows, and this number is the number of matrices. Yeah.
Okay. How about this? Can you take that 3-4 row ABC example and let's add another dimension to that. Like put a 3 in front or put a add like a 5 in front of that.
Okay. So yeah, the first number is um, this dimension.
It says they're printed layer by layer. So I think like
Okay. Okay.
so
Yeah.
3 is the number of rows, 4 is the number of columns, and 5 is the next dimension. There we end up having 5 of those.
Yeah. So it kind of ends up it kind of like grows out to the left.
Right, right.
The one to the direct left of the row symbol is always the number of rows or the number of columns.
And that's why I think like rows and columns, it feels like the documentation here doesn't talk about it in terms of rows and columns. It talks about it in terms of, you know, in terms of just simply rank, right? And it's like at some point that idea of rows and columns sort of breaks down a little, I think, right?
Yeah. Because like higher dimensions don't that's not really a concept. It's just we're adding dimensions, basically.
It's like a
What if we did?
three-dimensional Excel spreadsheet.
What if we had? What if we had four? Oh, we just get another group. Okay. There's like an extra group here.
Oh, right. It gives you a big space in the middle.
Yeah. Okay. So, I mean, yeah, I understand now what it means that this is different. This is something that doesn't seem to really exist in other languages. And it's kind of crazy that I'm talking about 4-dimensional data right here using just built-in functions.
Yeah.
Right? That's pretty nuts.
That's pretty wild, yeah.
I will say, I think it was a misstep to use a character called row when talking about dimensions where you're using the word row, ROW.
When you were reading that, I was like, row.
Yeah,
row.
yeah. That's, yeah. It doesn't matter what it doesn't matter what the rank of the right argument of row is. What? Right, okay, so this is 3.
What the rank of the right? So it's just saying you can use arrays as the argument on the right side of row, right? Of the row function.
Uh,
That's a cab.
almost, yeah. Matrices don't have to contain only scalars, like vectors and all other arrays. They can be nested. Okay, I'm sweating. Okay, so we got groups. We got this group data, right? Okay, yeah, this isn't crazy. We've seen this.
Yeah.
This is 2 and 3. We're just structuring it. Yeah.
Whoa.
Okay, I'm scared. Well, this is just the combinations of things we've seen. Just a really complex one.
Yeah. I mean, so that's pretty interesting. Like, at least to my newbie APL brain, that would take a minute to like really dissect that. But I do think it's kind of fascinating at a glance, you can tell that like the row function just being kind of in line like that, that feels to me like something that would take multiple lines in most languages, right?
Yeah.
The fact that there's a one function that then just takes like some arguments on the left, some arguments on the right, and produces multi-dimensional arrays is that's kind of cool.
Yeah, I would say so. Um, I feel like this would be really good for making like ASCII art.
Yeah, for sure.
Depth is general to arrays of any rank. The depth of an array isn't just the nesting level of vectors as shown previously, but of an array. So an array of depth -1. Wait. So an array of. Am I reading that right?
I think just depth 1.
Oh, okay. So an array of depth 1 matrices has depth 2, and a matrix of numeric vectors also has depth 2. A matrix of scalars will have depth 1, like any array of scalars. So the depth of this is 1. Right. Okay. Depth of this is 2. Okay. The depth of this is also 2. Okay. Of course, all arrays of uneven depth are dealt with in the same way as vectors. So this is negative because there's scalars. Wait, how is this different from the previous one? Why does this have a depth of 2 and this has a depth of -3?
because you have, so that first grouping, that one, the APL 360 has depth of -2, right?
Oh, okay, yeah.
And
This one.
so so overall you end up with depth of -3 because that's a nested group in there.
Right. Okay, that's what it is. I was just looking at the top layer and I was like, what? Okay. The depth of the previous example is -3. Man, he's gotta trust the system, man. Trust the process. APL has empty arrays. Theta. It's not really a theta. Is the empty numeric array, and empty array is the empty character array. The function row also has a meaning monadically when applied to only one argument. It returns the shape of its argument, the length of its dimensions.
Hmm.
Okay.
So
The
if you
length of its dimensions. Okay.
if you so that's kind of interesting. If you give it dimensions, it constructs an array. If you don't give it dimensions, it returns the length of the array.
The length of its dimension. Yeah.
The,
The length of
the,
its dimensions.
right. Not the number of dimensions, but the actual the shape. Yeah. Okay.
There is a distinction between single row matrices and vectors. What? Okay. Even if they look the same when printed. So, okay, yeah. So this is a matrix, and this is a vector. Oh no, this is just the row of it. This is just the row. Okay, so now
Oh, I see.
the row 1, 2, 3. Okay, so 1, 2, 3 is an array. This 3 row 1, 2, 3 is a or 1, 3 row 1, 2, 3 is a single row matrix. And these are different. Basically, what it's saying is that these have different uh, dimensions. They have different this. I feel like I kind of know what's going on, but like I don't know how to explain it.
Oh, so you can so you can reshape an array. This is kind of reminding me, have you ever messed with R at all?
No.
R has it's for, data science kind of stuff, and
Yeah.
it has all kinds of functions for dealing with tables and these kind of like multi-dimensional arrays with data and stuff like that. And it has stuff like this where you can reshape. I think even pandas and stuff has this where you can reshape the
It does. Yeah.
dimensions of an array.
Yeah. The length of the shape of an array is equal to its rank. Therefore, we can find the rank of an array with row, the shape of the shape. Since a scalar is rank 0, the shape of a scalar has length 0 and is an empty vector. Okay. Row ABC is 1. Okay. My brain's starting to give out on this, but I'm going to trust that this is correct and makes sense to everyone else.
Row?
You can use row to convert between a rank 0 scalar and a rank 1 vector. I feel like I'm getting to the point where it's like, is this like useful stuff? You know?
Yeah.
Okay,
Yeah.
we're at the end of this one now.
Yeah, I'm not totally following the end of that one, but hmm, you know, I think I get the gist. You can define arrays, you can get the shape of arrays, of multidimensional arrays, and you can reshape them. You can take the same data and put it into like different dimensions. But I think I know what you mean. Like, I don't know that I've ever had need to do that, to be honest, in the work that I do.
I want to look at functions a little bit real quick, just see what's going on with functions. Okay, we got dyadic, monadic. We talked about this. There's scalar functions and mixed functions. Okay, a scalar function will penetrate the array that it is applied to. I think I'm going to skim this a little bit. I just want to see what's going on in here. So this applies to the whole array, which is cool. You can negate each element in the array, just like that.
Oh, I see. As a prefix operator to the entire array.
Yeah. The structure remains the same. Okay. Okay, when a scalar function is applied dyadically, the scalars are paired up between the two arrays and the function is applied. Right, okay. So like same thing when you multiply, right? We saw this in the intro, right? Yeah.
Yeah.
They have to match number of terms.
That makes sense. The arrays have to have the same shape.
They can be complicated. Okay. Shapes of arguments need not match up exactly. Right. The scalar is distributed across all the scalars of an argument. So you can do this, doubles each element.
Yeah, that's cool.
Okay. Whoa. Additionally, scalars inside the arrays can be extended after the items have been paired up. Okay. All the arithmetic functions have a monadic definition: negate, reciprocal. Plus is the complex conjugate. Okay. Times returns the unit complex number in the direction of its argument. Raises E. Test them if you want. I won't. Mixed functions. Mixed functions apply to larger structures of the argument. For example, the rows of a matrix, or just take the entire argument. They can treat each argument differently in this respect. Monadic row shape is a mixed function. It returns the shape of its argument. We've already seen what row does, so yeah. But we're just saying that it's mixed because it applies to the structure of the argument. There are many functions. Okay, so I wanted to get to this, yeah. Dynamic functions are an APL expression enclosed in braces, where the left and right arguments are referred to by alpha and omega, the leftmost and rightmost characters in the Greek alphabet, respectively. For a monadic function, only omega is used. So we can define times as curly braces alpha times omega. DFNs, or dynamic functions, are anonymous functions. They don't require a name. This means that they can be used inline. Okay.
Again, that seems like a very, I don't know, kind of modern, high level kind of thing.
Some of this gets very I feel like you can get really lispy with this, like programming or programming type stuff going on here.
Mm-hmm.
Well, okay. So wait, okay. So okay, so actually let's this one first. So this took the rightmost function times 2, which would be 4 times 2, 8, plus 3 times 2, 6. 6 plus 8? Is that right? No. Oh, but then that added. Wait. Oh, that's not multiplication. That's exponents.
Right. That was throwing me too.
Okay.
So yeah. So.
Okay. So the formatting of this is very strange, right? The fact that one argument is on the left and one argument on the right. That's pretty weird.
Yeah. And then, right, and you're defining your function in line in the middle for an
Between the two.
infix.
Yeah, that's interesting. They can be nested as much as you'd like. Alpha and omega will always reference the arguments of the defined functions defined by the immediately enclosing braces. Wait. Oh, damn. So we have. This is. This is hard to read.
Yeah, I find that really hard to read.
That's very hard to read. Like right here, omega would be just whatever's to the right of this. Is that what's going on?
Well, we evaluate. So all the rules about evaluating right to left still apply, right?
I think so.
So we start with 4, and then so we first evaluate those. Oh no.
So omega is 4 and alpha is 3. But then for the outermost part, right?
Mm-hmm.
So I mean, so no matter what, this right here is 3 to the 2,
Mm-hmm.
and this is 4 to the 2. Uh, yeah, I don't know, man.
So that ends up being 25, right? Before the omega to the half is evaluated there, right?
What's 3 squared plus 4 squared?
Yeah, it's
Yeah.
25.
Yeah.
And then 25.
Yeah. So is 25 the omega here?
I think so.
What was the 43? So that'd be 25 to the. Can we okay? Let's come up with our own easier to calculate. Like let's make this addition, right? We should be able to figure this out. So that would be 5, and this would be 6. So then is it 11 plus 0.5? It is. Okay. Okay. That doesn't feel very good, but we got there.
I think, man, I maybe it gets easier. I do find that really hard to read though. You know,
Yeah.
one of the things I keep thinking about as we're going through this is, have you ever heard that there's like a saying that like code is easier to write than it is to read or something like that?
Yeah.
Um, that's what I keep thinking of during this. It's like
Absolutely.
maybe it gets easier when you know the symbols and after you're over the learning curve a little bit, but like I can totally see someone writing some APL as if they were writing like a regular expression, and they like it makes sense to them in the moment. But if
Yeah.
you ask them like a week later, they'd be like, "Oh yeah, I don't know how I came up with that."
Absolutely. Yeah. I feel similarly. I feel like I don't know. I there's really two, and maybe we're at a point now where we can like make some of these kind of criticisms. I guess you could say. First of all, I think it would like if you took a language like this, kept everything the same, but then like replaced the symbols with just keywords, and then maybe gave a little bit more rigid rules around some of these things, right? I think then you have something pretty cool. And I believe that's more or less what BQN is supposed to be. Let me see. I'm not sure right now, but BQN is like APL but easier, basically. And I think it's mostly just. I think it's the same thing, but like the symbols are like more like what you've are used to. So that's cool. Um, I guess you still have that problem of like people writing really, really advanced stuff that's hard to read.
That'd be interesting though. I mean, maybe in another episode we can take a look at BQN because like I almost feel like if you lose because I kind of have that same feeling. If you replacing the symbols with the keywords, I think gets you a long way toward readability. But like, if you get rid of that, I think you get rid of a lot of the like the feel of what APL is. If
Yeah,
I'm if
me
I'm
too.
at least as I'm seeing it so far.
Yeah. Um, Basically, what this part is that control flow is done in like the ternary way. There's not like a traditional if else. There's just like you do this with the diamond.
Okay. Wait, diamond is separates things on a line, but also is a ternary operator.
I guess, yeah. I guess when it's in this format, yeah. Uh, and you can do comparisons. See, like, okay, this is cool. So what we got right here is we got alpha is 10, omega is 12, and we're doing if alpha is less than omega, print alpha, else print omega. So if you, I mean, the fact that you can define this as a function and you could do this, like, I mean, like this example is kind of goofy, but if you do like, you know, if you start having like an array, uh, wait, did I have a mismatch? Oh, I can't just do that because that's not how it works. But I can define, like I can do like compare arrow this, right? And then I can do, oh wait, no. Wait, how do I do this? Yeah, I should be able to just do that, right? I just take the array, right? Save the value.
Can you d can we compare arrays less than or greater than?
Well, I thought it was going to compare each term. You know what I'm saying? The same way that like I can do this,
Right. And it
I
would,
can also do this.
huh? Yeah,
But
you're
in this
right.
case, I think like the alpha and omega thing is messed up, right? Because alpha is just this, or no, it's just this. Actually, I don't know. I don't know what's going on here.
Boolean single value.
It's saying Boolean singleton value is required. Oh, length.
I think your arrays are the right length though.
Yeah, they're the same length, but it's. What if I do like? Well, that shouldn't matter. I shouldn't have to name these. I should be able to just. I guess I just don't know what alpha and omega are right here. Boolean singleton value required. So for some reason, this isn't giving me a 1 or a 0. Oh, right, because it's giving me like 1 0 0 1 0. You know what I'm saying? That's what this evaluates to.
That's fine, but shouldn't it be printing out either one or zero? Shouldn't that function then give you an array an array with 5 elements that are either 1 or 0?
Uh, yeah, that's what a less than omega would be. Yeah, like a six ones and zeros. Okay, hang on. Inside a defined function, you can perform an if-else statement check. It takes the form this: A must evaluate to a Boolean singleton. So this must be a Boolean singleton whose shape consists of only ones. Right. Okay. So I don't know how you would apply it to like every element in an array like that. I'm sure there's a way. To perform a recursion, you can either use the name of the function or the symbol upside down triangle, which refers to the function it's in. If it's not named, you have to use upside down triangle, which is generally recommended so that you can rename the function without having to change its definition. So what is this doing? Oh, it calls itself here. Wait.
Whoa.
Okay. So fac is the name of the function, which we call here. Does that apply to? So omega is 5 when it gets called, right? So like 5 greater than 1, which is just 5 times 5 minus 1. Yeah, I see. Okay. Damn. Okay. So that's doing 5 times 5 times? Is that right? What's 5 to the 5?
5, 3,000 some. 3,125.
Is it 5 to the 4?
It's 5 to the 3. Oh, no. 5 to the 3 is 125.
Oh.
Yeah, I don't know what that is.
Right. Well, it also will add 1. Damn. I think the title of the video should be like, 1x developers do APL until they can't anymore.
It's okay. I feel like I kind of hit my wall, but I feel like I'm learning something here. This is interesting. I feel like my brain is expanding.
If you're not being challenged, then like you're not really learning anything. Let's go ahead. Let's hop over to Conway's Game of Life before we wrap this up.
Yeah.
So you're familiar with the Game of Life, right?
Mm-hmm.
I don't even remember it. You have a grid and like
you basically there's a set number of rules, and the rules are I can't remember exactly what they are, but pixels either come to life or die, and it's like a self-sustaining kind of thing. If you get your values right, the thing will just kind of like go on forever. Things will grow over here, and then they'll die over here, and they'll just like, and by grow and die, we mean like pixels will turn white or black.
Right. And so this is going to walk us through building that in APL. So first they define a board of 3 by 3, right? Which is centered in a 5 by 7 board, which is pretty easy to do here, right? It's just, hang on. This just prints 9 numbers. Many APL functions have mnemonic or visual clues to their meaning. In this case, we're going to, hey, this tells us this is iota.
Iota,
The Greek letter for I. Implements the index generator function, right? So we can just get 9. Okay, and then if we do 3, 3 row index 9, we can do 1 to 9 in a grid, right? We This is easy. We've seen all this. We know how this works.
Mm-hmm.
All right.
Beautiful and simple.
Dyadic row implements the reshape function as... Okay, yeah. We know this. Okay, now what the hell is this? Epsilon implements the element of function. This generates the starting bit pattern. Now we need to position it within our board, but first let's save the pattern in a variable named R. Wait, so what does epsilon do?
I think it plucks a single element from a list, right?
So what is this supposed to do? Okay, we got our 9. Oh shit. Ah, damn. Is that? Yeah. So, I mean, it's not changing our output in any way.
I don't totally get how, but I think the epsilon is you're choosing which bits are on to start with, right?
Okay.
So 2, 2, 3, 4, 5, and 8.
Oh, it's generating our starting bit. Okay. Okay. Let's keep going. So we need to get. Okay, we set that to the value R. Okay, you can display R. Yeah, know that. Now that we have our starting pattern, oh wait, what? But what is this? Okay, yeah. This is setting our. Okay, I see. I mean, I don't know why we have these numbers exactly, but I think I get what's going on.
I think in any time in Conway's Game of Life, you start with some bits on and some off, right? I don't know why they chose those, but
Oh, dude, I'm dumb. Yeah, that's just corresponding to like this is 2, this is 3, this is 4, 5, and this is 8.
yeah, right.
Okay, I wasn't. I don't know. I was having a moment there. Okay. The first step is to use the take function up to pad out the pattern to our desired size. Okay, we wanted it to be 5 by 7, we decided. So by doing 5, 7R, which is like 5, 7 this, we just make it bigger. The next step is to column center the pattern. With that, -2 phi. Is it phi? This is phi, right?
I think it's pronounced phi, yeah.
The high minus is used to denote a negative number. The symbol phi rotates along the last axis, which is the columns in an array of rank 2 greater. We're rotating around the rank? Does this make sense to you?
So this is the rule. This is like the rules that they've implemented. I'm not sure exactly what that means to rotate around the rank.
I mean,
But
I see that they're centering, right? They moved the center from here to here,
mhm.
and they did that with -2 phi. Oh, rotates around the last. Okay. So this is the columns. So it's -2 column. They're rotating -2 columns, which would be. So what if if I did +2? Yeah, then it rotates 2 to the left. See?
To the left.
Which is wrapping around to the
Oh.
other side, right?
Okay, yeah.
Okay. And that's just the same way that row worked. This is columns because it's like the only one.
Okay.
Okay.
Yep.
Next, we row center the pattern using the E function, which rotates along the first axis. So we have to use a different. Okay, phi uses the last X. Oh, okay. Okay. So, okay, yeah. So the number, okay, so if I did this, this would rotate 3 to the right. Is that correct? Yeah. Okay. Because it's just phi uses the last axis and E uses the first. Okay. Now we assign the board to the variable capital R. Okay. Okay. The rules for Game of Life dictate which cell lives based on the number of live neighbors. So our next job is to count the neighbors, and we'll do this by shifting the board by 1 unit in each direction and summing the results. What? Okay, okay, I think I give up. No, I wanted to do.
I got lost. Sorry.
Yeah, I think it shows, or maybe if I just jump to the end, because I've seen implementations of Conway's Game of Life in APL, and it's just so nuts. I'm wondering. I don't know if this is like the best way to do it, or if this is just like the way they chose to explain it. No, this isn't really. I thought I saw it.
Was there something at the top there? I think there was a link at the top of that Game of Life page.
I think this is just about
Oh,
the Game of Life. Oh, Conway's Game of Life in APL. Oh, it's a video. See if we can find his implementation. This is the same thing. I'm about to just find. Oh, I'm not even displaying the video I was watching. Damn. I think I saw a tutorial that shows this. Okay, here's one. You're seeing this, right? Yeah. So you can do like this, and this is this is one of the first things I saw when I was looking up APL, and I saw this and I was like, "What? This is a whole simulation program?" You know, like,
yeah.
Damn, dude.
That is pretty cool. I mean, here's the other thing too. I think if my math skills were stronger, I would feel more immediately at home with this stuff. You know what I mean? I feel like this language is obviously geared towards people who have pretty strong math skills and like a really good intuitive understanding of ranks and depths already. You know what I mean?
Yeah, maybe. Maybe we're just not that smart.
Well, definitely the case for me.
Oh damn, we've been recording for an hour and a half.
Yeah, it was a long one.
I don't know, maybe we should do this more. I feel like we were just both like engaged, we were locked in, we were in there, like that was fun.
I feel like I learned some stuff.
Yeah, I feel like we leveled up today.
I wouldn't mind revisiting this and looking at some of those newer dialects, the BQN. And,
yeah. Yeah. I believe they're all still kind of hobbyist type things, but it's interesting. It feels like there's really cool ideas in APL.
Yeah. I find the number stuff really kind of interesting. The way that it was like it didn't really care about the internal representations. The way I was saying like that seems sort of JavaScripty. I just think it's funny that like as we sit here in 2025, you know, the trend for I tend to equate like these older languages with being very, very low level, but like, a big part of like the things that Rust is trying to fix are these kind of like um, ambiguities around numbers in C and stuff like that. And meanwhile, you have these languages that were around at the same time that are just like, I don't know, give me a number, whatever. Like, I don't care.
Yeah.
I'll do whatever I want with it.
Yeah, I mean, I have to imagine there's like some performance trade-off there, or
Yeah.
memory. It's probably doing what you said. Like, it's probably just all floats under the hood, which is, you know, using more memory.
You probably wouldn't program an operating system in APL.
Yeah.
1x Developer Podcast.
Hey everybody, this is Colin. First and foremost, I want to thank you all for listening to this episode of the 1x Developer Podcast, and let you know that if you have any questions, comments, or if you just want to tell us about your day, you can reach us at X, formerly known as Twitter, at 1x Developer Podcast. We're also on YouTube at 1x Developer Podcast. You can email us if you're weird at 1xdeveloperpodcast at protonmail.com. And lastly, don't forget to follow, subscribe, all that stuff, so you don't miss any further episodes of the 1x Developer Podcast. Thanks so much. See you next time.